Good evening. Good evening, everyone. Welcome to a new series of presentations on the James Webb Space Telescope, which is offered to you by the McAuliffe Center. Good evening, everyone. Welcome. Sorry for the little technical echo. So again, this new series of presentation, which is offered to you by the McAuliffe Center for Integrated Science Learning. Hi, my name is Irene Porro, and I am the director of the McAuliffe Center. I am really delighted to be with you tonight to announce exciting new initiatives that will bring more and new programs to all our audiences. So first of all, let me tell you that our programs at the Framingham State Planetarium will resume in August. And our well-known monthly public planetarium shows will resume in September. So for all of you who are interested in our programming, I invite you to visit our website for a calendar for the upcoming in-person events hosted again in the FSU Planetarium. I think someone may be posting, or I'll post right now the link to our website here in the chat box. You can find there all our new appointments for in-person events in a planetarium. The other exciting news is that our online virtual presentation will also continue. So the focus of our virtual programs will be different. Explorations of the night sky will be done in a physical planetarium, as it should be. That's the best place for that kind of presentation. On the other hand, our online presentation will focus on specific topics in space science and astrophysics. And this is why, for example, tonight we'll start with a 3-session series on the Webb Space Telescope. So again, I just want to be super clear here. The McAuliffe Center will keep offering you not just the usual programs, but even more. In-person public planetarium shows in the planetarium and monthly virtual programs online. The topics explored will be different in person and online. So you are very welcome to attend both in person and virtual events. And I can promise you, you will never get bored. Of course, you can also choose the medium that you prefer to keep engaging with our great team of presenters. So now let's talk about tonight's event. As I mentioned, we are starting a special new free event series on the James Webb Space Telescope. This is very exciting because we are introducing something that many of you may have not heard so much about. So let me tell you just something to get you on the taste. Webb will be the largest, the most powerful, and the most complex space telescope ever built and ever launched in space. Its launch is scheduled, we hope, for the end of October, early November 2021, which is why we are starting introducing it now. Something else that is quite exciting is that the McAuliffe Center was selected to be one of the hosts of community events which will be celebrating the launch of James Webb Space Telescope. So we are starting tonight with this series, but this is just one of many initiatives that we'll host to celebrate this very historic, literally historic event. Now, Webb is an orbiting infrared observatory that will complement and extend the legacy of earlier space-based telescopes. Webb will push the boundaries of human knowledge even further to the formation of the first galaxies and the horizons of other worlds. Webb will literally open a new window on the universe and will allow us to see a region of the universe for the first time in the history of humanity. I just get goosebumps thinking about that. So what are we going to do? Tonight, we'll just start with an introduction to both the telescope and its science goals. Next month, we will focus more on the engineering aspects of the observatory, really to understand what spatial design and engineering strategies had to be developed to make sure that Webb can do the revolutionary research we are expecting it to do. Finally, in September, we will explore more in depth the scientific objectives of a telescope. What that means, we will explore more what is a new science that the researchers will be able to do with this telescope. So again, for the specific dates and times for these upcoming events, I really encourage you to check our website at the cm-center.org under Planetarium and Public Events. And the link was posted in the chat just a minute ago. All right. So for tonight, just one small housekeeping note. We will be using the Q&A tool feature on Zoom that you can locate in the bottom right on your Zoom window. Please keep your questions for the end of a presentation. It's a very rich presentation. Don't waste any second of it. But be ready to post your questions at the very end. We'll be absolutely delighted to address all your questions at the end of a presentation. And now, finally, tonight's speaker is John Sheff. John is currently a program facilitator at the McAuliffe Center. And he has been sharing with us stories of his explorations of remote parts of the planet and adventure travel journeys and mountaineering expeditions. His lifelong background as an amateur astronomer and space buff has him just as excited about the exploration of other planets and other worlds. So he's a perfect person for tonight's presentation. He is a NASA JPL Solar System Ambassador and an informal science educator. He is also a member of the Amateur Telescope Makers of Boston, and he operates the telescopes during public nights at the Harvard-Smithsonian Center for Astrophysics in Cambridge when they are held in person, of course. And just in case, should you be interested, he also regularly teaches a popular astronomy course at the Cambridge Center for Adult Education. So without further ado, John, welcome, and the mic and the screen are all yours.
Okay, can everybody see that?
Yes.
Wonderful, thank you. So what we're talking about is a very exciting development. I am very excited. It's been an exciting year for space exploration, and it's going to go out on a fine note. We're talking about the James Webb Space Telescope, which will be launched into space this fall, probably in October or November, by NASA and the European Space Agency. And I will be the first to admit this does not look like your typical backyard telescope. Yes, it has a parabolic dish up here. It has a secondary mirror here, but down here is something you will never see in a telescope that is used at night. And that's a sun shield, right? That doesn't make much sense in a telescope, but it does in this telescope because this is going to protect the telescope from the intense heat of the sun. NASA has actually launched a series of great observatories into space between 1990 and 2003. There have been 4 missions that have been very successful and resulted in incredible discoveries about the nature of our universe. 2 of these missions, Chandra and Hubble, are still working and streaming information back to us. But there's a new generation of space telescopes coming online. And the first one is going to be the James Webb, and we'll be talking about that tonight. The Hubble Space Telescope was launched in 1990, and it's been in space for 31 years, working fine with occasional glitches. There have been 5 space shuttle missions launched to service the telescope and improve it and keep it flying, and it has been flying ever since. One of the missions that was assigned to Hubble is to take an image of a blank area of the sky. This is a blank area of the sky about 1/10 the width of the full moon. It happens to be in the southern hemisphere constellation Fornax. And as far as we could tell with all our telescopes, there's nothing visible in that field of view. But when Hubble studied this area for 11 days, this is what it saw. Almost all of these objects you see are not individual stars, they're galaxies of tens of millions to hundreds of millions of stars each. And some of the smaller ones are actually up to 13 billion light years away from us. This is the deepest view into space that humanity has ever seen. And some of these galaxies were born less than 1 billion years after the Big Bang that created the universe. So if we look at this diagram, cursor, thank you. This is actually a timeline beginning at the birth of the universe and extending to the present day. In the present day, we see this type of galaxy that's something that we would recognize in our own time as typical spiral, elliptical, and irregular galaxies. And so we are here on the timeline. Hubble and the ultra deep field that Hubble made extends about this far back into the history of the universe. But notice, it's just short of showing us the first galaxies and the first stars that ever formed in our universe. We can't see that area. We can't see beyond where the Hubble ultra deep field is. And why not? Well, we really, really want to know what lies beyond there. And how has it changed over time? So we have to overcome 3 problems to see deeper than the Hubble ultra deep field. First of all, the problem is the earliest stars and galaxies are faint because of their immense distance. So what we need is a bigger telescope. Here you can see the size of the Hubble mirror compared to the size of the James Webb Telescope mirror. The James Webb has over 5 times the surface area of Hubble. And that means that it's a huge light bucket. It can collect much more light than the Hubble mirror can, which translates into the ability to see much fainter sources of light. So here's another comparison showing relative to a human being, the size of both mirrors. The second problem that we need to overcome are that the most distant objects are redshifted into the infrared. What do I mean when I say that? If you look at the distant galaxies near the beginning of time, all of them are emitting light, visible light, at the time it is emitted. But the universe, we know, is expanding. The space between galaxies, not the galaxies themselves, but the space between the galaxies is expanding. Space is expanding. And as that happens, the light rays on their way to us get stretched out to longer and longer wavelengths. And in fact, most of the emission of light that is visible light in a galaxy at the time it's emitted is infrared light by the time it reaches us here on Earth. So we have to be able to detect that radiation. Here's a schematic of the electromagnetic spectrum. The Hubble telescope, as you can see the narrow band of visible light and maybe a little bit into the infrared and a little bit into the ultraviolet. But what we want to see is here in the infrared. And that's what the James Webb Space Telescope will provide us. It can see into the near infrared and the middle infrared. And that's where the radiation that we're looking for will be found. And by the way, the problem is, why do we even need a telescope in space? Why can't we just build one on Earth that is sensitive to infrared? Well, we could, but this diagram shows that most radiation from space is blocked by Earth's atmosphere. This olive green area represents radiation that is blocked by the atmosphere. So gamma rays, X-rays, most ultraviolet light is blocked by the upper atmosphere. Most infrared light that we are very interested in observing from the early universe is also blocked by the atmosphere. The only thing that makes it down to the surface is visible light, which we see the stars by, and radio waves. So radio telescopes can function just fine on Earth, but we cannot see the band we're interested in with the infrared. That's why we need a space telescope. And Hubble is going to be, the James Webb is going to be fulfilling that role. The third problem that we have to overcome is that the telescope itself and the Earth emit most of their light in the infrared. Any object with a temperature above absolute zero emits its own radiation. Consider, for example, the sun, which has a surface temperature of 5,800 degrees Kelvin. It has an emission spectrum like this. It emits almost all of its light in a visible range. That's where its emission peaks. In a blue, green, red, the type of light we can see with our eyes. But an object that is cooler, like the, James Webb Space Telescope, if it was just floating in space left to its own devices, would be at about a temperature of 350 kelvins. And its radiation peaks way over in the infrared. Here you can barely see the visible light band crowded out towards the left. Most of it is given off as heat. So this is actually infrared radiation that the telescope itself gives off by virtue of its own internal heat. And that, unfortunately, is also the area, the wavelengths, where we want to see the early universe. It's almost as if you were in a crowded room and you're trying to hear conversations, and it's very noisy, and the signal of the conversation is very difficult to pick up because of the noise in the background. So what we have to do is actually make sure that the telescope is cooled. So here again is a schematic of the James Webb Telescope. This is the function of the sun shield. Everything on a sunward facing side can get warm, and the sun shield will insulate the telescope, the primary mirror, and the instruments on a cold facing side from any exposure to warmth from the sun. Here's another diagram. It shows the hot side, which can be allowed to heat up to 185 Fahrenheit. That includes the solar panel, the communications antenna, the computer, the steering and reaction jets. All of that can get as hot as it wants to. We don't really care about that. All those components are heat tolerant. But on the other side of the sun shield is the cold side, where we have our science instruments and our detectors and the mirror. And that's where we can cool down the telescope to such a temperature that it can see infrared radiation without swamping the signal with its own internal heat. The other reason the Space Telescope can be cold is its location. Now, Hubble is orbiting around Earth on a scale so small you can't see it. It's about 380 miles up. But the James Webb Telescope is going to be all the way out here at a point called L2, the Lagrangian point 2, which I'll explain in a moment. But it's 1.5 million kilometers, roughly 1 million miles more distant than Earth from the sun. So the telescope will orbit the sun along with Earth, but about 1.5 million kilometers more distant from the sun. It's not so much that that makes a difference in the heat from the sun, but the Earth and the moon, which are also sources of infrared radiation and heat, will also be behind the sun shield. So the telescope itself will never be exposed to any heat from the Earth or the moon or the sun. So it's going to take a bit of a journey. After launch this fall, it's going to take about 2 weeks to make its way over to the L2 position. And the L2 position is kind of metastable, and it will be orbiting in a ellipse around the L2 position, which will require just a minimum amount of attitude control and fuel and maneuvering fuel. It will be able to stay there for a very long time without being disturbed by gravity or any other forces. One of the disadvantages, though, of being that far away is that it won't be serviceable. Here's a picture of an astronaut servicing the Hubble Space Telescope in Earth orbit. The telescope was launched in a shuttle, and Hubble was serviced about 4 times, upgrading its equipment, doing routine maintenance to prolong its life. excuse me, and it is still working just fine as of this afternoon. But the James Webb, which is 1,000,000 miles further out from Earth, is not going to be serviceable by astronaut crews. So it has to deploy and work right the first time. What are the science objectives of the James Webb Telescope? It's a very big project, a very expensive project. It's taken a long time. So why are we doing this? Well, the first and main objective is to study the first stars and the first galaxies in the early universe. You can see that the James Webb Space Telescope will be able to see along this timeline back into the past all the way to what we call the Dark Ages. And the Dark Ages of the universe were dark simply because there were no stars to light anything up. But the first stars formed and clumped together into galaxies, and James Webb will actually be able to show us what the first stars and first galaxies looked like in a first within the first billion years of the Big Bang, much further than the Hubble Ultra Deep Field. A second science objective will be to study the formation and evolution of galaxies. This shows galaxies as they appear in a present day. This is a beautiful spiral galaxy. This is a giant elliptical galaxy. These are what galaxies look like today. But early galaxies looked radically different from this. And they underwent a process of evolution, which I'm going to show you on this video. This is a computer simulation of early galaxy clustering and formation. They're kind of featureless at first, but they gradually merge and collide and develop structure that more and more resembles galaxies that we see in the present day. Here you can begin to see some spiral structure developing. But this is just theoretical modeling. We don't know that that's how it worked because we haven't seen that far back in time. Now the telescope, the James Webb, will be up there able to pick up very sensitively infrared radiation. So the question is, now that we have this telescope up there, what else can we do with it? And one of the things we can do is to study the birth of stars and protoplanetary systems. This is a familiar photograph to many of you, I'm sure. It's the Eagle Nebula, also known colloquially as the Pillars of Creation. And this is taken by Hubble in visible light. But when we look at this same image in infrared light, also taken by Hubble, remember it has a tiny bit of range in the infrared, so it can see this. Now we see all these sources of cooler stars that emit infrared radiation but are not visible in invisible light. So we can see a lot more detail. We can see formation of dust clouds and gas and solar systems much more clearly in the infrared. Here's a new word for me, propylenes in the Orion Nebula. And what are propylenes? Propylenes are our solar systems and star systems that are in the process of formation. Their dust and gas clouds are just gathering together under the influence of gravity and forming solar systems. And this is how our solar system formed. So it's very important for us to understand how solar systems form, so we can understand how our own solar system formed and how others nearby may be forming. And yet another objective of the James Webb Space Telescope is characterizing the atmospheres of exoplanets. Now, in the past couple of decades, we've found literally thousands of exoplanets, planets that orbit around stars other than our sun. And the James Webb isn't really designed to look for exoplanets. We found plenty of those, but what the James Webb is uniquely capable of doing is characterizing the atmospheres of exoplanets. In infrared light, a planet will appear much brighter relative to its star than it does in visible light. So it's much easier to pick out the planet, to image it, to study its atmosphere. And the James Webb may be able to identify molecules that emit their radiation in the near and mid-infrared in planetary atmospheres. This is a diagram showing Earth and its atmosphere and some of the molecules in the atmosphere. We have water vapor, oxygen, methane, carbon dioxide. All of these are byproducts, for the most part, of living things. Most of these gases are unstable over geological time periods, so they must be replenished from new sources. And one of the most common sources on Earth for these molecules is biology, is living things. So we call these biosignatures. And here's a hypothetical exoplanet in which the James Webb may be able to detect methane, carbon dioxide, water vapor, etc. Now, none of these by themselves make a conclusive case that there is life on this exoplanet, but taken together along with other evidence, it will show that this is definitely a planet that merits further research using other techniques that may actually allow us ultimately to conclude that there could be a habitable environment on these exoplanets. So at this point, I am going to introduce a poll. And the question is, which targets would you like to look at with the James Webb Space Telescope? First stars and galaxies, the evolution of galaxies, the origin of planetary systems, or biosignatures from exoplanets? I'd like to see a vote, and let's just see what people are more interested in. So far, we have one vote for first stars and galaxies. Okay, the votes are coming in. Excellent. Okay. Yep, please cast your vote if you have an opinion. If you were in charge of assigning time to the James Webb Space Telescope, what would you like to study first? Okay, I'll give it about another 10 seconds. Okay, that's interesting. The first stars and galaxies seem to be the choice. So that's great, and we will take that into account for our next presentation. We will see if we can get more excitement on that subject. So thank you very much for the vote. And at this point, I am going to show a sequence of launch, the launch of the James Webb Telescope, which will be happening this fall. So this is a launch from French Guiana near the equator. And the rocket is being launched from there because that's the spaceport that the European Space Agency, our partner in this, uses. And it's their rocket called an Ariane 5. And here we go, boosting out of the atmosphere. The solid rocket motors on either side are adding to the momentum of the main rocket. They've burned out of fuel. They're being jettisoned. And the main booster is activated. The payload fairing is uncovered. We don't need that protection anymore from the Earth's atmosphere. And the first stage is jettisoned. At this point, the telescope is cruising along with its second stage in Earth orbit. And we have second stage ignition. At this point, the telescope is being launched out of Earth's orbit and into the trajectory to L2. Here it's rolling a little bit to distribute the heat of sunlight evenly without stressing any particular component too much. And here the second stage is jettisoned and the telescope is flying free. Here a solar panel is deployed for electrical power. We will be deploying antennas, other instruments. Here you can see the sun shield palette being deployed. And the sun shield itself is gradually extended. These are multiple sheets of foil that are thinner than a human hair, but they are extremely strong and extremely good at insulating the telescope. Here you can see that there are several layers of those being deployed. And now the telescope mirror itself is going to be assembled. This is way too big to fit into a rocket, so that's why it has to open up like an origami here once it reaches its target. And it is ready for business. I think it'll take about an initial 6 months of testing and deployment before it's actually ready to do science. So that is our presentation for today, but I'd like to invite everybody to join us for part 2 of our series on a James Webb Space Telescope. The next session will be Wednesday, August 18th, and we'll talk about how the telescope will function in order to perform its mission. We'll get a little into the nitty-gritty details that we kind of glossed over today. And on session 3, Wednesday, September 15th, we'll talk about what we can expect the James Webb Space Telescope to actually find. And please join us on Friday, October 15th, when we'll have an in-person event in our planetarium at the McAuliffe Center at Framingham State University. And last but not least, we're going to have a launch party to watch the James Webb Space Telescope begin its mission. And we will announce the date on that as soon as NASA announces the date for us, and we'll be able to expect the imminent launch. Okay, so with that, I end my presentation, and I want to thank everybody in the audience. And I think we are now ready for some questions and answers.
John, thank you. This was such an informative presentation, so exciting. I know that every time I hear you talk about James Webb, I get more excited, and I cannot wait for that launch to happen. Again, please enter your questions in the Q&A box. And we will, John, if you don't mind, I can, as they come in, I can read the questions so that you can address them. Maybe you can also stop sharing, or maybe share.
Yes, I will stop sharing.
Right, I guess for now. But again, this was really exciting. We have already a first question. I would like to encourage everyone to enter any question they have. There is no small question or big question. We'll try to address everything comes through at the best of our abilities, right? So the first thing is a very important question. What is gravitationally special about L2? What is special?
That's an excellent question. And what it is it is a location in space where the gravitational forces of the Earth, the Sun, and the outward momentum of the telescope as it orbits the Sun all cancel. And it's a stable location because it's almost as if the telescope was in its own solar orbit at that distance, but because the Earth is there in addition to the Sun, the gravitational force of the two allows the telescope to orbit at a greater distance than Earth by itself would. So it's a gravitationally stable place where gravity and centripetal force cancel each other out.
Yeah, and in astronomy, people always look for very stable places where to put telescopes. So in space, sometimes it's very difficult to find orbits where there are not too many shaking or maneuvering that needs to take place. Wow. Okay, well, okay. There are a lot of questions about Lagrangian points.
Okay.
Related questions. Aren't there other L points that NASA could have chosen?
There are definitely other L points. L1 is between the Earth and the Sun. So it's on the opposite side of Earth from L2. And NASA could have chosen that location, but then Earth would have been directly in the field of view of the telescope. So that wouldn't work out too well. There's L4 and L5, which are positioned 60 degrees ahead of Earth in its orbit and 60 degrees behind Earth in its orbit. Those positions would have worked as well, but they're a little further away and they're harder to reach, and it would require more power for communications and data transmission. There's also an L3 point, which is on the opposite side of the Sun from Earth, but that would have been even further away.
I feel like I would like to say, and I'm sure we'll learn more about Lagrangian points in the presentation that we will offer in August, right? But another question about the design of the telescope, how was the shape of the mirror design? Why that shape?
Why that shape? Well, the mirror is what's called a segmented mirror. There are hexagonal segments. And the reason for those is you may remember the telescope is too big to fit into the nose cone of a rocket. It has to unfold. So that design, the segmented hexagonal mirror, was the easiest design to create that would be reliable and easy to unfold and also easy to very accurately align. The focus of the telescope has to be very precise, and those segments have to be aligned very carefully. And the hexagonal design allows each segment to link to its neighboring segment to achieve the proper alignment.
Mm-hmm. Yeah, something else extremely important in astronomy alignment. Still about the mirror, why is a mirror or both gold-plated?
Why is it gold-plated? It's actually made of a material called beryllium, which is not that common, but it's something that is very, very light, which is important when you're boosting something into space, and yet it's stronger than steel. And it's also thermally inert, which means it doesn't expand and contract very much with changes in temperature. The gold plating on the surface was just a very thin film to ensure that the infrared gets efficiently reflected. But that's a great question.
Oh. All right, so my goodness, 6.5 meter diameter of gold plate. That's still a lot of gold, I can imagine.
It's a lot of gold, yes.
And now, John, I'm so happy to see this question because we were discussing this afternoon. You know what is coming. You know, who is James Webb? Why is this telescope called James Webb Space Telescope? I know there is an interesting story about that.
There is an interesting story. Well, James Webb was not an astronomer. He didn't have anything to do with this telescope. He wasn't even a scientist, to be truthful. James Webb was an administrator of NASA in the 1960s, from the time the moon landing project was started until I think he resigned or retired just several months before Apollo 11 landed on the moon. So he was there when President Kennedy announced the goal of a human landing on the moon. And throughout the 60s, he was an organizational genius. He was a very good manager. He created basically whole industrial empires dedicated to creating the Saturn V rocket and the Apollo missions that would land men on the moon. So he was a NASA administrator. And there's an interesting story about that because the James Webb Telescope is actually a cooperative project between NASA and ESA, the European Space Agency. And when NASA decided to name this telescope after James Webb, that was kind of a unilateral decision. The Europeans were not consulted on this. and they probably weren't too happy to have this telescope that they helped build named after an American administrator that had nothing to do with science. But sometimes that's the way NASA functions, and these things can't be helped. Politics always enters into the picture.
At least though, it's a short name. Everyone is going to be able to say Webb. And when we will say Webb telescope, you know, in a year from now, we will all know very well at least what the telescope is and does, right? We may or not remember James. There is one more very interesting question that is about the lifetime in communication between Earth and the Webb telescope. Is that important because it's so far away that, right? Is that important as far as the operation of a telescope is concerned?
Well, let's do a back of the envelope calculation. We know that the time delay between the Earth and the Moon is about 1.5 seconds. This telescope is about, let's see, 1 million miles. The Moon is 250,000 miles away. So I'd say about the telescope is, say, 40 times further than the Moon from Earth. So it would take maybe a full minute for a signal to reach James Webb and come back. Now, is it important? Well, not really, because all of the observations from James Webb are programmed in advance and sent up to the telescope well in advance of the time of the actual observation. And the data doesn't need to come back live. The data can come back whenever the telescope is not busy doing something else. So the time lag is much greater than it is to communicate with something at the Moon, or certainly Hubble, but it's not a factor in terms of doing the science at all.
All right. Yeah, I thank you for such a quick calculation. And yeah, very important point. As long as there are no human beings involved at that distance, it's really not a big problem. That's great. Right. I know it is 8:30 and we probably need to bring things to an end. Again, apologies to everyone for a couple of technical hiccups we had at the start, but I love, John, how you say it. Is like when you deal with a space program, one way or another, there are technical issues. Ours were much easier to solve, of course. I would like to remind everyone that you can find out about both our in-person events coming up and our next 2 events on the Webb Space Telescope here virtually online on our website. And I know that Suzanne just posted it again on the McAuliffe Center website under Planetarium and Public Shows. So I hope you can all check that out. Again, we have in-person activities starting again in August, and then starting on the regular basis for our public shows in September. But we will continue every month providing a free virtual presentation. And for the next 2 months, again, we will focus on James Webb Space Telescope. So thank you so much to John. This was a great presentation, and thank you all for attending tonight. Have a wonderful weekend.
Thank you all.